He's feeding back.
I've been asked on the spur of the moment to introduce your speaker this evening. His name is Preston Nichols.
Hold it a second. Wait for us, will you?
You said go. Again, I'm introducing your speaker for tonight. His name is Preston Nichols. His title is Ancient to Modern Detectors and How They Interface with Scalar Waves. And I'll bet most of you understand that a lot better than I do. Preston Nichols.
All right, this presentation is going to actually have three parts to it. First, we're going to talk about something very boring, detectors, starting with coherers, going up to regenerative detectors, through to heterodyne type detectors. We have about roughly almost 60 slides of material from older textbooks, which will be included in the proceedings because they're out of print. You can't get them. You have to find an old library somewhere to find them, and they're not that readily available. The second part of this will be due to interest in how the 3D sound system in the minefield amp operates. I'm going to be explaining that as far as the block diagram, how it functions, what the different pieces do. We're not going to go into circuitry of how to build this particular piece of equipment. And then if you look over there, you'll see we have a section cordoned off with wire, not ropes, because I don't own any rope. All I have is wire. And in there, we have basically a minefield system amplifier coupled into a musical source. Happens to be a reprocessed digital CD player, where I'll explain how that works and what we've done with that as we go into the explanation on it. And what will happen is it will spread out an etheric field, and in a sense it can sit in there and read the music, look into the music, get the emotion of it and all this type of good stuff that the experientialists love. So we will now start with detectors. What is a detector? Basically, it is a device that converts one form of energy into another form of energy. How it is usually used in your radio is it takes your radio wave that comes in your antenna and converts it to the audio wave. In other words, if you take your radio signal coming in from the antenna and put it into your speaker, your audio amplifier, all you hear is a nice big loud hum, because that's all that's coming in at the audio range. But now what you do is you take your signal, let's say it's 1 megahertz on the broadcast band, you amplitude modulate. That means you vary the modulation up and down with the audio. That detector will pick up this variation and supply the audio to the audio amplifier. So as you see, your detector is the most important part of your receiving system. Now, detectors respond to three kinds of functions, actually. They respond first to power. In other words, in this function, if you take the ordinary incandescent light bulb, hook it across your antenna, if you got enough energy coming in your antenna, the darn thing will light. That's saying there's power there. You just detected the power. You tell you got something there. This is generally what is picked up by the Hertzian receivers. Your radio, your TV sets pick this up. Although it's infinitesimally small, there is enough power there. Now, you have the next function is basically what I call a potential function. What this basically is, anyone knows anything about electronic theory, if you have your voltage and your current at a 90-degree phase angle, the power is zero. So that's just potential. It's the potential to do power if you can rotate it back in. This is what a lot of people call a scalar wave, although technically it's not a scalar wave. Now the third kind of function is a time stress. This is basically what you get by stressing the zero-point potential in the vacuum. If you go through myriads of mathematics that Paul Dirac did in the 30s on electron activity in a vacuum, you'll see that he ends up at the end of all this stuff a function which is a function of time to space. In other words, it's f of t. It's the integral of f of t ds. S is space. In other words, what he's saying is now you can control time by stressing the 0-point potential of the vacuum. Of course, you take a vacuum tube, it's got a vacuum in it. It's got an electron stream. If you up the electron stream enough, you're going to stress the vacuum. When you exceed the 300 volts per meter function that Dirac calculated, you'll find that you'll generate a rip in time, so to say. Now, this is my theory. Okay, now let's do a little bit of review of how dimensionality is a la Preston-Nichols. We are in the electron domain. I've said this many times, but I'll say it once again quickly. We are in the electron domain. If you go one orthorotation, hyperspatial rotation, 90 degrees, what happens now is you get a particle with no power. That's a magneton, or the magnetic particle. Now, if you rotate another 90 degrees in the same direction, 180 degrees, everything's reversed. So what happens? The electron becomes a positron. That's your antimatter or mirror image world. Now, I believe this to be basically set up something like this. I like the Hindu diagram that I've seen. This is us, and this is them. This is electrons. I'll call that minus, and this is positrons. Now, around this, you have a shell, keeping this separate. You know what happens if you bring positrons and electrons together? It all goes up in the big bang, and the whole thing starts over again. So you have us. Now you go 90 degrees, you get into this shell world, or a flat world. Then you go another 90 degrees, you get into the reverse world. Now, as I've said many times, you know, the power of a Hertzian wave is basically...
Would you just pick that cord up, junction, and stick it in your pocket, please?
Sure. If you take an electric field and cross it with a magnetic field, the complex conjugate, you get Poynting's vector, which is saying that the integral is equal to the power and the instantaneous power of the wave. And then you integrate that over the full time period, you get the power in a function. Now, he's saying E. He doesn't specify whether it's E plus or E minus. That's saying the wave is basically a cross between the electron and the magnetic domain. Now, all the math holds true if you use a positron. This is what is commonly called a scalar wave. This is your first order hyperspatial wave. This is what we call a potential wave. Okay, now, as I explained before, if you go here, 90 degrees, you get into a domain with no power. And then you go 180 degrees, you're totally out of our domain. Now you got nothing but scalar canceled fields. You know, plus, minus, cancel to zero. All right, I gave you that little bit of background on electrical operations. Now, I will say this. Many people talk of scalar waves. What is a scalar wave? True definition is canceled fields. Now, I've found so many people talking of scalar waves as being a catch-all for anything that's not Hertzian, is not a power wave. In other words, what's basically happening in this world is you draw a line here. This is Hertzian, all of this is scalar. It's not scalar. That's why I'm calling it potential and time stress. So I wish to clarify that point. Now we go into detectors. If we cut the lights off and we go over to the screen, we can start with our detectors. This is just a background information that I just gave you on what detectors do.
No. Second from the end. Far left.
All the way over.
That's it. All the way over to the end. Far left.
Okay. You see, the first book, if you look here, yeah, focus is wonderful. If you look here, 1915. This is wireless telegraphy. We go to first chapter 6, detectors. Here you got thermal detectors. This is a little piece of wire that when it gets hot, it changes resistance. All you do is you pass a small current through this to measure your resistance. Then you put your RF through here. As the RF gets stronger, this heats up, and you got a detector. This detects power. This won't do anything for you in the etheric functions, or what's commonly called the scalar functions. You have many different forms, thermocouples. You see you have here I believe this is a platinum strip on copper. That will make a potential difference. As you heat the thing further, it will produce a voltage. You see they're pumping it with heat to get it hot enough so it's producing a voltage. And by putting your RF across here, it'll get a little hotter, a little cooler, and you'll get a change in that voltage. And you'll get basic rectification. So, as it says here, you can read this in the proceedings, but basically they're saying the relative importance of a thermal detector is it tells you got power, that's all. That doesn't do you a hill of beans on your etheric functions. Now, the next class of detectors was basically discovered by Marconi. It's a magnetic detector. This is a simple, basic form of a magnetic detector. You got an input coil wrapped around an iron bar, an output coil that goes into your receiver or your telephone headpiece or your audio amplifier or whatever you want it. Now you take this piece of magnetic material and you spin it. What this is going to do is this is going to make and break a magnetic circuit. Due to the velocity of the magnetons flowing in here, this will actually generate a time dilation in here, and you will convert potential functions into a usable current that come out here. Of course, we have many different kinds of magnetic detectors. This is Marconi's magnetic detectors. The difference is it has like a tape running through it very slowly. Your input coil, your output coil, and he puts two magnets to polarize the thing. This is not well understood kinematically how this thing works. I believe personally that as this tape moves through, it is creating a magnetic potential field on the tape as it moves. And you're varying that potential field. So this will pick up a electric potential, or it's possible for a magnetic potential going directly in here to change it, the magnetic potential field. Now the next class of detectors is imperfect contact detectors. That's your coherer. What your coherer is basically is a glass tube, two plugs. These are conductive, maybe gold, silver, iron. Now, hung in between these, you put filings. What are the filings made of? If you read through this, you'll see that they use, I don't remember exactly what it is, but they use nickel filings, iron filings. They have formulas for this, and it just keeps building and building and building. And as you can see, you go through, you get different forms of coherers. Basically, what the term means is when the signal goes through, all these filings congeal, and all of a sudden it conducts. Of course, this is a one-shot thing. You have to hit the thing, to break the filings up, and then you're ready to receive another signal. Mercury coherer is the same idea, except they're using the molecular tension of mercury to change resistance as the signal goes through the detector. You have graphite and carbon coherers. That's basically a carbon microphone. You can use your telephone as a detector of high-level currents. You have a cross between a chemical detector and a point contact and a coherence. Who knows what that is? Back in these days, they had all sorts of weird detectors. Next is electrolytic detectors. They called them in those days anti-coherers, because what happened is when the signal went in, the resistance would go up, not down. This, of course, is commonly talked in psychotronics as a psychic energy detector. I'm sure you've all seen somewhere the tube, the cup filled with salt solution with two rods sticking in it. You pass the current through it, measure the current flow, and as you concentrate, you can change that current flow. This is picking up a potential cloud, because when you go to, that focusing is wonderful. Yeah. When you go into a detector type thing, you have your electrolyte and your two electrodes. And what happens here is you flow a current through here, and then you put your RF circuit in, And as your RF signal goes in, it changes the conductivity of the electrolyte. How that happens, basically, electrolyte is a polarized molecule. That means it separates. Inside that molecule, you'll get an electron cloud or an ion cloud. This is a potential cloud. One potential function can influence the potential cloud, change the conductivity, and you got detector action. I'm going through first detectors, and I'm going to go deeply into what a detector actually does. You have the barettas, which is like another thermal detector. Won't go backwards.
No, it does not reverse. You want to go?
Yeah.
Reverse it?
They have something called a liquid baretta. I've yet to figure out what they're talking about here. From what I can gather, it's a combination of point contact and a chemical detector, you know, your old chemical cell. Next, we go to the crystal detectors. This is what we commonly know as the crystal radios. What this is, you have a piece of galena, a piece of graphite, any sort of crystalline substance. You take a very fine point and you sort of let that set spring action on the crystal. And then you have the body of the crystal as one terminal, and then you have the point as another terminal. That basically looks something like this. Yeah, I guess this is lit enough. Your basic receiver looks like this. You have your selection, your coil, your LC network. Then your crystal. This is the diagram of a crystal. That's the point, and that's the crystal. We still use this today. And then you go into your receiver, your telephone receiver. I know my drawing leaves a lot to be desired. I apologize. Then you ground this, and you hook your antenna here. And as you tune this capacitor, you select the station here, this detects it. This is the way the circuit generally looks. Of course, you usually have a bypass capacitor here to get rid of the RF that leaks through. You'll see here they use carborundum, titanium dioxide, molybdenite. I think I said that right. Copper pyrites, chalcopyrite, magnesium dioxide, iron pyrites. Just about any crystalline surface will, on a point contact, detect. Your gas detector, I'll talk of gas detectors later. Now, of course, you go to a vacuum tube. Let's leave vacuum tubes till later. This book leaves a lot to be desired. I just included it to get the feel of it. Okay. What is detector action? Here's your modulated waveform. These little pieces in here is the very high frequency radio frequency. This is the modulation envelope here. What you're doing basically is through some means, let's see if we can focus it a little better. Yeah, that's better. You take the carrier energy and you make it high on the peak of the sine wave and you make it low on the valley of the sine wave. This is normally your audio function. What you do, your simplest detector is just basically a rectifier. See, there's your tuned circuit, there's your diode, and there's your output. What you do, you take this, you chop half of it off, and then you integrate this thing, and you come up with a DC voltage that follows this voltage, as you see here. They took this, they chopped half of it off. All it is a common rectifier. Now, of course, depending upon whether you're using a point contact that generates a potential field around the point contact, or you're using a vacuum tube detector that generates an electron cloud, which is a potential cloud. This type of detector, a potential function comes through here, gets tuned, will affect the electron cloud, and you'll affect the output signal, and you'll get a variation due to the potential. Of course, in a vacuum tube, if you now feed a secondary signal in here, stress the vacuum, now you can pick up a time stress coming in here. So this type of detector is useful for most of the hyperspatial waves that I know of. There may be more. You know, hyperspatial waves, the order can go up many, many, many times. And again, you can see they're taking different functions and showing how they average out. I'm not going to go deeply into this. People interested can look at this in the proceedings. All these slides will be in the proceedings. I had to apologize for the smudges on the slides. It's clear. It's just I had reflections all over the place. Again, you see you got full wave for the engineers. You know, I'm sure you engineers know the difference between a full wave and a half-wave rectifier. Let's not go into that. I don't want this to be boring for the people who don't fully understand this stuff. And we have different forms of detectors. You can take a triode and connect the grid to the plate, and you got a detector, and you know, all this kind of stuff. It just goes on and on. You see conduction curves, and you know, let's not go into that here. RF filter circuits, that's something very strange in itself. Automatic grid bias. This is all pure electronics. It's very well described here in these books. It's all based on vacuum tubes, which is what I think is going to be the coming trend in psychotronics. All these slides will be printed in the proceedings just as you see them. Yeah, with all the captions and everything you need. As you can see here, if you take the grid of a vacuum tube, you got a diode, basically, from the grid to the cathode. You can set up this RC network, which the DC voltage or the detected signal will develop across the resistor capacitor combination. Now, that DC voltage will return to ground means now you're modulating the electron stream, and you got amplification here as well. You see you got many different ways of doing this. You can go to a triode, you can go to a tetrode, you can go on and infinitum with this thing. And you can see it does the same basic thing. It takes your modulated envelope, cuts it in half, and sums it. It does all the same thing. Now, and now they're telling you, yeah, you can have RF appearing here, so you got to put a pi-type filter to get rid of the RF. Most people not even that considerate what it is. Now, the next type of detection is heterodyne detection. What is a heterodyne? You mix two frequencies together. You multiply them one times the other. You get the sum and the difference of the frequencies. It's shown right here. You get 8 cycles, you get 12 cycles. You'll get 4 cycles as a resultant here. That's what they're showing here. It's all explained very, very heavily in this book. Now, what they're telling you is this is the BFO of your old shortwave receiver. You got your AM rectifier type detector. And what you do is you take this oscillator running at the input frequency of the detector, and you bias the detector on. Of course, when your input signal goes on, 0 beats, you got 0 cycles coming out, and as the audio varies, the sidebands go through, and that sort of thing, you'll get a detected audio output here. The interesting here, this is a bias detector, which means now you got a constant current flow going between on, off constantly, and this is going to stress the vacuum, and this is very sensitive to time stress, this type of detector. This is a type of regenerating detector. Your regeneration is here. You see, they couple these coils to this coil. I won't go in deeply into the physics behind this. People interested, read, or ask me if you have to know today. Now you have regenerative detectors. Basically, what you do here, it's very simple. This circuit here forms the oscillator. This is the bias carrier type thing, and you put your signal into the oscillator. Your mixing is done in the same tube with the oscillator. The interesting thing you can do here, you can vary the amount of regeneration, which means you either go on or off, and as you vary the amount of regeneration, you can take this thing to where it's just below oscillation. It becomes very sensitive. At the point where it's below oscillation due to negative resistance functions and the Barkhausen criteria, what happens is you get a negative reactance here, a negative resistance function here, cancels out the coil. The coil's DC conductance resistance, and what happens is the Q of this coil, since you cancel out the DC resistance, and the Q is basically the inductive reactance over the DC resistance. The DC resistance goes to 0. The Q of this thing goes to infinity, which means the bandwidth goes to 0. or you get very, very narrow bandwidths with one tuned circuit. But the interesting thing here is when you take this to where it's just breaking into oscillation, now what you got is noise spikes causing the tube to go into conduction, saturation, on saturation. Excuse me. Out of saturation, the tube cuts off. As I've explained in previous lectures, when you take a tube between cutoff and saturation, at that point you're really stressing the vacuum in the tube, and you're making the tube very sensitive to these subtle energy functions. This is why a lot of times I personally use a regenerative type detector, because the thing is constantly oscillating between saturation and cutoff, but it's not oscillating to the point where you lose the sensitivity of the detector like you do in a heterodyne type detector. Now, there are many methods for controlling the amount of regeneration. In other words, how much feedback from here to here. You increase the feedback. At some point, this tube's going to break into oscillation. As you decouple, it's going to break out of oscillation. They talk of basically, as you see in further slides, of loosely coupling coils, tightly coupling the coils. You can change the gain of the tube by doing many different type of things, which we'll get into a little later. Super regeneration. The old regenerative detector has the problem of basically running in and out of oscillation. The thing is very unstable. Major Armstrong got the idea, let's make this thing oscillate at a lower frequency and feed that in and cut the tube on and off. What this does is the tube never starts to oscillate. The minute the tube starts to oscillate, it's cut off. So you're quenching the oscillations in the tube. This is super regeneration. This is not as good for the etheric energies as the plain regenerative detector by very closely controlling the amount of regeneration you're putting in. People may remember at the Atlanta conference, I demonstrated a regenerative receiver that should have no gain that was picking up on small pieces of wire from all around the world. That's picking up the etheric functions. And as we ran the regeneration through, you got different portions of the etheric functions. I theorizing at this point, I can't prove it, that you're getting different kinds of hyperspatial waves as you change your regeneration. Regenerative or detector is very, very interesting. Autodyne basically is another form of regenerative detector. That's where you have a mixer and an oscillator and a heterodyne detector in one vacuum tube. It's the same thing. This is more theory on the squelching of the super regenerative circuits. Now we go to Terman's book. This one was published in 1937. Out of this, we start with electron oscillating detectors. These are very interesting because here's the magnetron with circulating currents inside there. Now you get time warps besides time stress going on inside the circulating currents in a magnetron type thing. I have covered magnetrons before. Let's not go into it heavily here. But they're called electron oscillating detectors. And again, we show you two different forms for heterodynes. You mix this frequency, you get an envelope that shows you the mix of the two, and you get the sum and the difference here, this sort of thing. That's redundant to what I said before. This shows it better. This is more mathematics. Here, you got basically a tube with an oscillator and a mixer. This can be used as a detector. You can put your audio circuit here. In 0 beat, you got a heterodyne detector. Varying the coupling of this coil, you can make it a regenerative detector. Now, over here, you'll see ways to get back to regenerative detectors. Control the coupling. Or control the amount of plate voltage on the tube. This is the two most common ways of controlling regenerative detectors. You'll see I have a lot of information here for regenerative detectors, which I won't go through at this time, but people are welcome in the proceedings to read this.